Hello, my name is Kim Haynes and I'm a Principal Product Marketing Manager in the Chemistry Technology Center at Waters Corporation. Thank you for joining me today, and I would like to spend some time over the next half hour or so helping you to unlock the power of mixed mode solid phase extraction and really use that to fine-tune your solid phase extraction methods to make them highly selective and highly reproducible. The ideal solid phase extraction method needs to be something that's easy to implement and transfer from laboratory to laboratory. It also needs to be reproducible, which is one of the most important aspects of any method. It needs to be fast, and ultimately it doesn't need to be overly complicated. It just needs to be good enough to achieve the goals in your analysis. For the purposes of the work I'm going to describe today, we're going to use the Oasis family of sorbents. So Oasis consists of two reversed phase sorbents, which are Oasis Prime HLB and Oasis HLB. We won't really talk about those today. There are also 5 mixed mode sorbents, and those include Oasis MAX and WAX. Those are a strong anion and weak anion exchanger. And Oasis MCX and Oasis WCX. Those are a strong cation exchanger and a weak cation exchanger. There's also an Oasis Prime MCX. We won't be talking about that one for today's purposes, but the Oasis Prime family was actually something designed to help simplify solid phase extraction, and I encourage you to check those out in other presentations or on our website. All of the Oasis sorbents are based upon the Oasis HLB sorbent, which is a water-wettable sorbent. HLB stands for hydrophilic lipophilic balanced copolymer. And what this really is it's a combination of N-vinyl pyrrolidone and divinyl benzene. That gives this sorbent the functionality to retain polar compounds very well, but it also gives a very strong reversed phase retention. Since it is a copolymer, it's stable across the pH range of 1 to 14, giving it a lot of flexibility. It's reversed phase, giving high recoveries for acids, bases, and neutrals. And here's an important aspect of this sorbent is that since it is so water-wettable, it actually allows you to completely eliminate the condition and equilibration steps that you'd typically have to do when doing solid phase extraction with silica-based sorbents or even some other polymeric sorbents. The other important aspect of this is that it won't dry out under vacuum or positive pressure, which gives it a really high level of reproducibility. As a sorbent sits under vacuum or positive pressure, sometimes you have to wait for all of the wells or all of the cartridges to process, and that can introduce some variability into your analytical results. But with the Oasis sorbents, since it doesn't dry out and it is so water-wettable, you actually see a very consistent and reproducible result from sample to sample. So the Oasis HLB, as you see in the center of the diagram here, is actually the basis for all of the mixed mode ion exchangers as well. What I mean by that is we take Oasis HLB, which is that copolymer, and then we actually functionalize it with an ion exchanger. If we look at the top, Oasis MCX and Oasis MAX, you'll see that we take that Oasis HLB backbone and then we add a strong ion exchanger to it. So in this way, it has that mixed mode functionality where it gets the reversed phase retention from the Oasis HLB portion, and then we add on the ion exchange functionality with the ion exchanger. If we look at the bottom, you'll see Oasis WCX and Oasis WAX. These also have the reversed phase functionality of the Oasis HLB backbone, but then we add a functionality for the weak exchanger. For example, the WCX, we add a carboxylic acid. And in this way, we can manipulate the charge of the sorbent based on the pH of whatever solution is flowing through that particle. So on the top, with the Oasis MCX and MAX, those sorbents will always be charged. On the bottom, with Oasis WCX and WAX, we can actually turn the charge off on those particular sorbents depending on the pH of the solution flowing through. And we can use that to our advantage when we're developing our mixed mode solid phase extraction protocols. So why would scientists use mixed mode solid phase extraction? It's actually a very, very powerful tool because it enables you to have the highest degree of specificity, giving you orthogonality in your SPE method. And as I mentioned previously, what that means is that you can get both reversed phase retention and ion exchange retention in your solid phase extraction method. And that allows us to really fine-tune our method to retain acids and wash away things like bases or neutrals or other contaminants within the sample, or we can selectively retain bases by cation exchange, washing away other impurities that might be in that sample, or we can even design a method to collect and isolate both acids and bases. And when we understand how these sorbents work, it allows us to really fine-tune that method and collect both of them independently of each other and then pool them later. So I'd like to start the scientific kind of understanding part of this just by getting us all on the same page. And we'll start with some basic ion exchange principles. Let's think about a basic compound. A base is actually a proton acceptor. At basic pH, our base will be unionized in its neutral form. And as we move to acidic pH, the base can become ionized. I also want to point out the pKb. And this is the point where 50% of the base would be ionized and 50% of the base would be neutral. So we generally like to try to work at a pH that is at least 2 units away from the pKb of the compound so that we can ensure that we have full functionality in one direction of being ionized or the other direction of it being unionized. If we think about an acid is actually a proton donor. At acidic pH, the acid is in its unionized or neutral state, and as we move to basic pH, the acid becomes ionized and gives up its proton. The pKa of an acid is the point at which 50% of that acid is ionized and 50% is unionized. So just like I described with the base, it's always a good idea to try to work at a pH that is 2 units away from the pKa in either direction so that we can make sure that we're working with our compound in a fully ionized or unionized state. When we developed a method to be used with the mixed mode ion exchangers, we tried to make it as simple as possible to follow and figure out which method is going to be the best for your analytes of interest. So I realize this slide might look a little bit complicated, but we're going to break this down and make this very simple and very easy to understand. You'll see here the 4 different Oasis mixed mode sorbents across the top. And all of those are used with one of 2 protocols. So let me break that down a little bit more for you. If we focus in on Oasis MCX, which is the strong cation exchanger, and Oasis WAX, which is the weak anion exchanger, we can use both of those sorbents with protocol 1. And those will allow us to capture our neutral compounds, our bases, and any strong acids that we may have. We see here, if we focus in on the sorbents of Oasis WCX, which is the weak cation exchanger, and Oasis MAX, which is the strong anion exchanger, we can use those sorbents with protocol 2 to collect our neutrals, our strong bases, and our acids. I'd like to take some time now to run us through some experiments with those 4 different mixed mode ion exchangers because I think that will really help you understand what's happening at each step of those protocols I just showed you. And then you'll really understand how you can use these sorbents and unlock the power of mixed mode solid phase extraction. So we'll use 4 different analytes with different functionalities. We'll look at imipramine, which is a base with a pKa of 9.4, ibuprofen, which has a pKa of 5.2, valethimate, which is a very strong base. It's a quaternary amine with a pKa greater than 12. And we'll look at a very strong acid, decane sulfonic acid, with a pKa less than 0.5. So what we'll do based on what we know about those compounds, we'll choose the appropriate sorbent, use the appropriate solid phase extraction method, and then evaluate them based on the recovery. All of these analytes were diluted 1-to-1 with 4% phosphoric acid, and we do that for two reasons. One is that we want to dilute or reduce the viscosity of the sample itself, and that acid actually helps to break up any drug protein binding to boost our recoveries in the analysis. So here I'm just showing you a picture of the four analytes that we're spiking into the ret plasma. And you can see structurally they're quite different. The imipramine is our basic compound. The valethamate is a very strong base, a quaternary amine. The decane sulfonic acid is a very strong acid. And the ibuprofen is our regular standard acid. So let's get started understanding how mixed mode solid phase extraction works. And we'll start with imipramine, which is our basic compound with a pKa of 9.4. And since we know this about our compound, we can choose Oasis MCX as the mixed mode ion exchange sorbent because that works well for bases with a pKa between 2 and 10. And for that, we'll apply Protocol 1 and see what we get. So I'm going to take you step by step with what happens at each step of the process. If we think about the mixed mode ion exchange sorbent, Oasis MCX, as I mentioned before, this is a very strong cation exchanger. So regardless of the pH, whether we are at pH 0 or pH 12, this sorbent is always going to carry that strong charge. So the sorbent is always ionized at this point. Now if we think about our basic compound, we talked about bases earlier, and we remember that at basic pH, our base is in its not unionized or neutral condition. But as we move to acidic pH, our base becomes ionized, and we can use that knowledge to develop our method. If we think about the interaction then between the Oasis MCX sorbent and our basic compound, we see that at acidic pH, we can actually lock our basic compound onto that Oasis MCX sorbent. But as we move to basic pH, we can actually neutralize our base and elute that and unlock it from the Oasis MCX sorbent. So when we apply the methodology here, we'll see that we load our pretreated sample, and as I mentioned earlier, we dilute that 1-to-1 with a 4% solution of phosphoric acid to disrupt protein binding and reduce the viscosity. We then wash with 2% formic acid. And what that enables us to do is lock on our basic compound by ion exchange, but at that point we can remove the polar and acidic interferences because our basic compound is charged and locked onto the sorbent. We then wash again with 100% methanol, and this allows us to remove any neutral compounds, acids, or hydrophobic unlocked interferences. So we are washing essentially with 100% organic, which is a really strong wash protocol, but we're keeping our base locked onto the sorbent. Then we can elute in 5% base and methanol. And what that allows us to do is actually neutralize the base. So we're unlocking the ion exchange mechanism, but we're also overcoming any reverse phase functionality because we're doing this in 100% methanol. And that allows us to get a very great recovery of 108% for our imipramine, and we have success in our method. Now let's take a look at how this would work with Oasis MAX, which is our strong anion exchanger. And for this example, we'll use ibuprofen. It's an acid with a pKa of 5.2. So again, for this, Oasis MAX is perfect. It works very well for acids with a pKa between 2 and 8. And we'll apply Protocol 2 for this solid phase extraction cleanup. So let's take a look at our Oasis MAX sorbent and understand how this works. As I mentioned previously, Oasis MAX is a strong anion exchanger. So no matter what the pH of the solution running through the sorbent, it's always going to be charged. At acidic pH, at basic pH, we cannot turn the charge of this sorbent off. Now let's think about our acidic compound. We talked about acids earlier, so we know that under acidic condition, our acid would be in its neutral or unionized state. But as we move to basic pH, that acid becomes ionized, and now it's able to interact with the charged Oasis MAX sorbent. Let's see how our acid and our Oasis MAX sorbent combine to give us retention. As I mentioned previously, an acid under acidic conditions, it's in its unionized or neutral state. But as we move to basic pH, we can actually charge that acid and get that to retain on the Oasis MAX sorbent. Now let's take a look at that Oasis MAX sorbent and protocol 2 so we can understand what's happening at each step of the protocol. Again, we're going to load our pre-treated sample, which is diluted 1:1 in a 4% phosphoric acid solution. That reduces viscosity of the plasma and also helps to disrupt protein binding. We wash with 5% base, and what that allows us to do is remove the polar and basic interferences while our acid is charged under basic pH and becomes locked onto the sorbent by ion exchange. We then can wash or elute, if we're collecting a neutral compound, with 100% methanol. And what that's going to allow us to do is remove any neutrals or bases and hydrophobic unlocked interferences. But our acid's going to stay firmly in place on the Oasis MAX sorbent because of the ion exchange functionality, even though we're running 100% organic through the sorbent. Then in the final elution, we'll elute with 2% formic acid and methanol. That allows us to neutralize our acid by going to an acidic pH, but we're still overcoming any reversed phase retention that would be going on by using that high concentration of methanol. And that allows us to get a very good recovery of 100% and have success with our ibuprofen sample cleanup. Now let's move on to the weak exchangers, and we'll start this discussion by looking at decane sulfonic acid. This is a very strong acid. The Oasis WAX sorbent is ideal for this, as it's very good for very strong acids with a low pKa of less than 1. If we were to try doing decane sulfonic acid as a sample cleanup on the Oasis MAX, which is the strong anion exchanger, that decane sulfonic acid would lock onto that sorbent and we'd never be able to get it off because it's a very strong acid and the Oasis MAX is a very strong ion exchanger. So therefore we need the weak exchangers when we have very strong acids and bases. And for this example, we'll use protocol 1 and we'll kind of walk through this step by step so you can understand what's happening at each step of the process. If we take a look at Oasis WAX, or our weak anion exchange sorbent, in this case, we're actually able to manipulate the charge of the sorbent itself. So at basic pH, our Oasis WAX would be in its neutral state. But as we move to acidic pH, we can actually turn the charge of the sorbent on, and that's how we can get ion exchange interaction. Now if we look at our strong acid, remember here we're looking at decane sulfonic acid. Since it is a very strong acid, that acid is going to be charged no matter what the pH of the solution that it's in. So we can use these two mechanisms together to create our solid phase extraction retention. This means that at acidic pH, when our WAX sorbent is charged, that's when we can get retention of our decane sulfonic acid. If we want to elute our decane sulfonic acid, what we need to do is actually move to a basic pH to neutralize the Oasis WAX sorbent and allow our strong acid to be eluted from the Oasis WAX sorbent. So here's what that method looks like. Once again, we're loading our pre-treated sample that's diluted 1:1 with 4% phosphoric acid. And then we wash with 2% formic acid. And what that allows us to do is make sure that the Oasis WAX sorbent is charged. And that allows us to remove polar and basic interferences, again, while charging the sorbent to make sure that we're locking on our acid. Then we can wash with 100% methanol. That allows us to remove neutrals, basics, and other hydrophobic unlocked interferences. We can then elute in a solution of 5% base and methanol. This allows us to neutralize the Oasis WAX sorbent and allow our decane sulfonic acid to elute by reverse phase functionality off of the sorbent. So what we see here is a very high recovery of 94%, and we have success in our cleanup of the decane sulfonic acid. The same idea holds true when we look at Oasis WCX, which is the weak cation exchanger. And here we'll use that with volethimate. It's a quaternary amine, a very strong base. WCX is very good for bases with a pKa greater than 10. So this is an ideal scenario, and we'll walk through each step of the way so you can understand how this works. So if we take a look at Oasis WCX, this is a carboxylic acid. So at acidic pH, our sorbent won't be ionized, it'll be neutral. As we move to basic pH, we can actually charge that carboxylic acid and our sorbent becomes ionized. If we look at our strong base, we would see that whether we're at acidic pH or neutral pH or basic pH, our basis as a quaternary amine is always going to be charged. So we can use these two functionalities together to develop our solid phase extraction method. What we see here is that when we work at basic pH, when our carboxylic acid functionality on the Oasis WCX sorbent is charged, that's where we can get retention of our strong base. As we move to acidic pH, we neutralize the charge on our Oasis WCX sorbent, and we're able to elute our strong base from the sorbent. Now let's walk step by step through the protocol to make sure that we understand what's happening at each part of the protocol. Again, we load our pre-treated sample that's been diluted with 4% phosphoric acid. Then we wash with 5% base, and what that allows us to do is remove polar and acidic interferences while making sure that our strong base is locked onto the sorbent by ion exchange. Since we're working at basic pH, remember that carboxylic acid is now charged. We can then wash with 100% methanol, again a very strong wash, to remove neutrals, acids, and other hydrophobic compounds and other unlocked interferences while keeping our base securely locked onto the sorbent. We then neutralize our sorbent by eluting in an acidic solution in 100% methanol. That allows us to elute our base and also overcome any reverse phase retention that may still be there and get very successful retention of our final compound. And we see here 106% recovery, very acceptable and very good performance for our basic compound. So what I've really tried to illustrate here is that the Oasis 2x4 protocol, meaning the two methods and the 4 different sorbents, can really be used to help streamline solid phase extraction method development, which can reduce ion suppression, it can increase your specificity, and increase your sensitivity. And these two protocols and 4 sorbents provide great recoveries for the wide range of analytes that we looked at. In this prior example, though, we were looking at things where we know whether the compound is an acid or whether it's a base, so we were able to choose which sorbent would be the best one for our method. But what happens when we have mixtures of compounds, or we have unknowns, or we have zwitterions, and we don't really know how our analyte is going to behave? I want to show you a method development scenario for those types of compounds. So in that kind of scenario where we have mixtures or we have an unknown or a zwitterion, we can choose to work with something like a sorbent selection plate or sorbent selection cartridges. And what this is a plate or set of cartridges where we actually have some of each of the 4 mixed mode ion exchange sorbents that I talked about. So if you focus in on the middle here, you'll see a plate that has wells of both the strong and weak ion exchangers all across the plate, so that we can follow that 2x4 protocol and very quickly and easily figure out which sorbent we need to use going forward for the method for that particular compound or mixture of compounds. Our sample analyte that we'll look at for this experiment is cephalexin. It's in a class of antibiotics, and it is zwitterionic, meaning that it has a carboxylic acid and amine moieties. It's really difficult to predict in these kinds of scenarios whether the base will be more active, the acid will be more active, or which sorbent we would choose based on this knowledge to get a really successful solid phase extraction method. The problem here really is that since we have the zwitterion, we're unsure of the compound behavior, but we need a really fast SPE method development for this particular compound. So the best idea here is to use the OASIS sorbent selection plate to evaluate all 4 sorbents using both protocols, and then we'll be able to quickly identify which way we should move going forward. So that's exactly what we're able to do. If we take a look again, backing up to the 2x4 method development protocol, as I mentioned, we have a 96-well plate that has all 4 of these sorbents you see across the top. We can apply both protocols to the same 96-well plate and then collect the eluents of each of these sorbents and be able to identify quickly which one works the best for this zwitterion. When we do that and collect the eluates from each one of those sorbents, we see that very clearly OASIS MCX was the best sorbent to clean up the cephalexin, the zwitterion. We see here that we get about 100% recovery, which is very good. When we compare that to the OASIS WAX, MAX, and the WCX, and you can see that since the ion exchangers are designed to retain or wash away different compounds given their different protocols, you can see OASIS MCX versus MAX in ELUTE 2, we had a much lower recovery, whereas with OASIS WAX and WCX, we actually saw that compound coming out in the ELUTE 1, or that first wash step with the 100% organic, and we saw, again, much lower recoveries. But with that 2x4 protocol, we were able to very quickly hone in and figure out which sorbent was going to be the best one for this particular unknown. So in conclusion, I've tried to show you that the OASIS sorbents provide a path to a very simple, fast, and easy approach to solve the problems inherent to complex sample matrices. Really helps you find that needle in the haystack when you need to do a good solid phase extraction cleanup. And the water wettable characteristics of OASIS allow you to skip the condition and equilibration steps without sacrificing the confidence in your analytical results. The OASIS 2x4 method protocol is a very straightforward and easy approach to doing method development when higher levels of cleanliness, specificity, and sensitivity are actually required. And I think we showed that for unknown compounds, mixtures of compounds, or zwitterions, the sorbent selection tools are a great way to quickly and really efficiently figure out which sorbent you need to use to develop your solid phase extraction method. I'd like to thank you for joining us today, and please feel free to reach out to Waters Corporation if there's anything we can do to help you in your solid phase extraction methods. Thank you.